Hello and welcome to part B of our Unit 4 review series. This time we are going to talk a little bit about electromagnetism and how that relates to electricity and electricity production. So first up, I wanted to review a little bit of what we did with magnets. So as you can see, this is a bar magnet. It has a south pole and a north pole, and it creates a magnetic field. You can kind of see the lines of the magnetic field generating outwards. So these red little lines here, that's supposed to represent the red end of a magnet. The white one represents the south end of the magnet. And so when I hold the south end of the magnet up to the compass, you can see that the compass responds to it, where the little north arrow will actually point towards the south end of the compass. And likewise, when I move the compass, if I try to put the red end next to the red end of the bar magnet, match north on north, it actually gets pushed away. So this is just a lot like our law of charges that we learned in the last topic, where like charges repel, different charges attract, and so we can kind of see that same thing happening with magnetism. And these two phenomena are actually very closely related. So the next thing we want to look at is how a magnet can actually induce a flow of electrons in a coil of wire. One of the things that Faraday discovered was that when you move a bar magnet through a coil of wires, the magnetic field actually kind of pushes around electrons as it moves through. If I just leave the magnet sitting there, nothing happens. There's no current flow. In order for this current to get induced in the coil, I actually have to have some motion there. The bigger the motion, the more energy is actually generated, the more electricity current flows. Now, the other interesting thing about this is I don't have to just move the bar magnet through. I can move it around, down here on the bottom, for example, and it generates some electricity. And the other thing is I can actually move the coil around the magnet. So the motion's totally relative. I can move the magnet through the coil or the coil through the magnet, and either way I will see that same induced electrical flow. Now, if I wanted to make this effect more pronounced, I can do things like adding extra loops, and that definitely increases the amount of current that's generated. And I can also increase the or decrease the size of the loops so that everything's more tightly wrapped. If I make the loops really big, you can see the current not quite as big. And likewise, if I decrease the number of loops, there's not as much electricity being generated this way. The reason why this is important is because these effects are totally reversible. For example, if I wanted to put an electric current through this wire, instead of, say, attaching it to a load like a light bulb, it generates a magnetic field. You can see here that there's actually an electric field being generated by these moving electrons. If I just turn the current off, there's no magnetic field. When I turn it on, the magnetic field gets stronger. If you compare that with the pickup coil, the magnetic field was actually created by the bar magnet, and the wire here just responded to that magnetic field. Here, when there's electricity flowing, when you reverse the situation, it creates the electric field. And if I move my compass around, you can see that it actually responds to the compass just like it's a magnet. So we call this an electromagnet. Now, if we really wanted to truly make this an electromagnet, what we would need to do is actually put a soft piece of iron inside this coil. And what that would do is then induce the magnetic field within the iron. The iron would kind of constrain or limit that magnetic field, and it would then be able to act as a magnet. And the same things apply that applied for the pickup coil. More coils equal more strength for the magnetic field. You can see the arrows fading in and out as they get brighter and darker. And this is what's going to let us build things like electromagnets, a magnet that you can control. Another interesting thing to notice about this electromagnet is if I reverse the flow of electricity, the magnetic field also reverses. And this is going to come into play when we start discussing how our motor operates. So there, it's reversing, and then it's going back up the other way. So there's a few advantages to using electromagnets. One of them is you can quickly reverse the current, which is good if you're making an electric motor. And the other one is that you can completely turn it off, which means that you don't have to worry about an electric current being generated. Permanent magnets are permanent because they're always on. An electromagnet is considered temporary because you can turn it off and on at will. Now, the last thing we need to take a look at with this lab is that if we can find some way to actually move this magnet without having to wave it around, like here we can only make electricity when we move the magnet back and forth. If we want to generate electricity consistently, what we need to do is find a way to move the magnet for us rather than us having to do it. If we look at this arrangement, here we still see our permanent magnet. Here's our coils of wire connected to our load. And what we want to try to do is find some way to move this magnet so that it can lead to an induced electrical charge or current in this coil. So the way we do that here is we hook this up to some water. And as the water falls on this water wheel, it spins the magnet, it causes motion of this permanent magnet, which then induces current flow in this coil. The more motion we have, the greater the output, and we can turn it off and on at will. Now, the one thing that's important about this is if you look at the motion of the electrons, they're kind of going back and forth relative to the change in the north and south poles on the permanent magnet. When a current moves back and forth like this, we call it alternating current. So this is how we would create alternating current. And this is all going to come back when we start to look at motors and generators in a little bit more detail. So this brings us to generators and motors. Just to recap, magnets can make electricity flow through a coil of wire. They do this through a process called induction. The changing magnetic field pushes electrons through the loop, and we can reverse that. If we push electrons through the loop using electricity, like in this case on a battery, we can actually induce a magnetic field. When we induce a magnetic field using electricity, we call that an electromagnet. An electromagnet is a strong temporary magnet which is made by wrapping a coil of wire around a piece of iron and running a current through it. We can change the strength of this electromagnet by increasing the voltage in the battery. We can run more current through the battery. We can also increase the number of loops of wire going around the nail. And we can also use bigger pieces of metal as opposed to smaller pieces of metal. And the last thing we talked about that's going to bring us to our next topic is that if we can move a permanent magnet next to a coil of wire connected to a load, we can actually turn that into a generator. We can generate electricity, turning mechanical motion into electrical energy. So, an electric generator is a device that turns mechanical energy into electric energy. So a DC generator is basically a generator that produces direct current. We call this a dynamo. If we reverse a DC generator, we can actually turn it into a DC motor, much in the same way that we can use a bar magnet to make electricity, or use electricity to make a magnetic field. We can use a electric current to produce motion using a DC motor. So a DC motor, instead of turning mechanical energy into direct current energy, like we would find in a generator, it turns direct current electricity into mechanical energy. So the way it does it is basically through an arrangement of 5 parts. The first part is the source, basically the thing that's providing the electricity. It's we kind of might know it as a battery. It might also get electricity from plugging into the wall, but wherever the source is, that's going to be your source of electricity. The second thing that we're going to see are the brushes, and these are basically little pieces of metal that allow electricity to flow from the source into the commutator, or the split ring commutator. The split ring commutator basically allows for the flow of electricity in one direction. Now, the thing that makes this unique is that this commutator is actually going to be spinning around. So as it spins, every 180 degrees, these two sides of the commutator are actually going to get reversed. And what that means is that the direction of electricity through the next part 4, the armature, is actually going to change depending on which side is connected to the negative terminal of our source. Now, as we saw in our lab, when we change the flow of electricity through an electromagnet, it changes the magnetic polarity. And this is important because we're actually going to see this work drive our motor. This is what's going to make our motor work. So we've got our permanent field magnets, which are outside the armature. And as the armature, which is the coil of wire that rotates through a field magnet, changes the direction of its magnetic field, it's going to push off of and be attracted to different sides of the permanent field magnet. So the field magnet basically makes a steady magnetic field. It pushes and pulls on the changing magnetic fields in the armature, and this constant pushing and pulling on our changing magnetic field is what generates our mechanical energy, our motion. So if we could actually hook this armature and split ring commutator grouping together along, say, some sort of shaft, we would have a motor that could make energy in the form of motion, like, say, driving wheels or the blades on an electric lawnmower or a fan, something like that. So here we have a representation of a motor. Over here we have our source, positive terminal, negative terminal, and it's connected to our split ring commutator, and the brushes basically provide that point of contact between the source and the split ring commutator. And so right now, the electricity flows from our negative terminal, goes through into this side of the split ring commutator, flows through our armature, comes back into this side of the split ring commutator, and then goes back out the other side. Now what we're going to see is that this produces an electric field that's actually kind of drawing it up towards this side. This side's getting drawn towards the other, and you have that direction of motion. Now, right here, once it gets past, this side is actually attracted to the red part of this magnet, which means it's going to be repelled from this green side. So what we need to do is actually reverse the flow of electricity. And the split ring commutator does that by having this little gap in there. That little gap breaks the flow of electricity. Momentum carries the rest of the armature through with no magnetic current, or no magnetic field. And once it gets to the other side, the split ring commutator has actually reversed the flow of electricity. So now it's still flowing through the same direction relatively, but compared to where it was 180 degrees ago, the magnetic field's been reversed. So now, rather than being repelled from this side actually wants to come back up to the top, this side wants to go back down to the bottom, and the process repeats over and over. So we have a break in current, reversal of the magnetic field, attraction, repulsion between two sides against the field magnets, and the process goes on and on over and over again. So this brings us back to the DC generator. The DC generator basically has the same parts as our DC motor. However, it functions backwards. It turns mechanical energy into direct current. So much in the same way that we can reverse produce an electric field from moving electrons, or we can move electrons by moving a magnet through our coil of wire, we can actually do the same thing with our motor. So in this case, instead of being connected to a source, we're going to connect it to a load. And what we're going to do is, instead of using electricity to produce changing magnetic fields in our armature, we're actually going to physically move our armature by connecting it to some sort of source of mechanical energy. In the example on our lab, it was a water wheel that actually produced that change, like that. It could be a wind turbine, it could be a steam engine, anything like that. But what we've got is some sort of motion that's causing this armature to turn. As this armature turns, these permanent field magnets are going to cause the flow of electrons through this coil of wire, just like in here. As this thing moves, it's causing a flow of electrons. So in this case, we've got a bar magnet changing the coil of wire, but we could reverse that. With our motor, we're actually moving our armature, our coil of wire, relative to a stationary field magnet. So the two processes are completely reversible. So we've got our load, and this is the thing we're going to be powering, but all the other parts are the same. We've still got brushes that are pushing up the split ring commutator. The split ring commutator still allows electricity to flow in just one direction from the armature. And we've still got this armature, which is the coil of wire rotating through the field magnet that's basically generating our flow of electricity, our currents. And so the field magnets in this case are basically the thing that are pushing and pulling on the electrons inside the armature and causing electricity to flow. So in effect, mechanical energy becomes electrical energy. So we've got our different generators, our different motors. In this case, we've basically got two types of current, AC and DC. We've got our generators, our motors. They have different purposes and different roles. So an AC generator, that's basically what we're going to find in most of our power plants. These things make alternating current. It's very effective in transmission across large distances. By the time it gets to our home, however, it's been stepped down in voltage. We're still going to use it to run our large appliances, but rather than convert it to a different kind of current like DC, we're just going to actually use an AC motor. So we're going to hook an AC motor up to an AC power supply created from an AC generator. DC current is usually used in small electronics, computers. It's used for emergency power, backup generators. And since it's the current that's produced by batteries, we're going to find DC motors most often in things like power tools or anything that has small motors in it, like toys, even things like cell phones. The little vibrating motor inside a cell phone that makes it buzz is actually just a little motor that rotates and gives kinetic energy, mechanical energy to your phone to make it move or vibrate. So that's it for this topic, generators and motors. If you have any questions, please leave them in the comments section or find me before the test, and I'll be more than happy to help you out.